AdaCoder is a novel adaptive prompt compression framework designed for visual programmatic models, which generate executable programs to answer questions through large language models. The framework operates in two phases, compression and inference. In the compression phase, a set of compressed preprompts is generated, each dependent on a specific question type, from a preprompt that describes all API definitions in the Python language with example snippets of code. This approach enables the framework to reduce the computational complexity associated with visual programmatic models. In the inference phase, given an input question, AdaCoder predicts the question type and chooses the corresponding compressed preprompt to generate code to answer the question. This adaptive compression framework addresses the limitation of requiring long input prompts to provide sufficient API usage details to generate relevant code. By employing a single frozen large language model and predefined prompts, AdaCoder negates the necessity of additional training and maintains adaptability across different powerful black box large language models. Visual question answering aims to provide responses to natural language questions given visual input. However, end-to-end learning models face limitations, and visual programmatic models have been introduced to overcome these limitations. These models generate executable programs specifically designed to answer questions, but they require long prompts to enable the large language model to understand API usage. AdaCoder's adaptive prompt compression framework reduces token length by 71.1% while maintaining or even improving the performance of visual question answering, as demonstrated in experiments with ViperGPT. The framework's ability to operate with a single frozen large language model and predefined prompts makes it adaptable across different powerful black box large language models, providing a more manageable and transparent inference process. AdaCoder is a novel framework for adaptive prompt compression in visual programmatic models, or VPMs. This framework operates in two phases, compression and inference. In the compression phase, AdaCoder generates a set of compressed preprompts, each tailored to a specific question type, from a preprompt that describes all API definitions in the Python language with example code snippets. In the inference phase, AdaCoder adaptively selects a compressed prompt by classifying the question type and generates a Python program to answer the input question. The authors highlight three key contributions, proposing AdaCoder as a novel prompt compression framework for VPMs, defining and formulating all procedures of AdaCoder with a single frozen large language model, or LLM, and demonstrating the effectiveness of AdaCoder over the state-of-the-art ViperGPT model on 3 VQA datasets with GPT and Claude. AdaCoder reduces the token length of input prompts by 71.1% while maintaining or even improving question answering performance. This is significant, as visual question answering, or VQA, has seen the introduction of end-to-end models that process multimodal inputs, with recent models incorporating attention modules to enhance individual feature extraction. Large-scale pre-training has become critical in improving the performance of these models. Visual programmatic models, or VPMs, have gained research attention for their ability to generate programs to answer questions based on visual input, leading to more manageable and traceable inferences. In the context of LLMs, code generation has been a focus area, with models like Codex and CodeLlama demonstrating proficiency in multiple programming languages. Black box LLMs like GPT 3.5, 4, Claude, and Gemini integrate extensive knowledge from a broad spectrum of domains, allowing them to generate code and understand complex instructions. Reasoning and interpretability are important considerations when integrating LLMs into real-world systems, with various prompting techniques improving interpretability. Prompt compression strategies, such as fine-tuning of LLMs, token reduction, and token merging, have been developed to minimize the number of tokens processed during inference. The AdaCoder framework introduces a novel approach for adaptive prompt compression in programmatic visual question answering. It consists of two phases, compression and inference. In the compression phase, a set of compressed prompts is generated using a large language model, LLM, with two instructions rewriting API definitions and writing code snippets specialized for each question type. This phase is run only once to prepare the compressed prompts. In the inference phase, the framework adaptively selects a compressed preprompt to generate Python code for visual question answering. The preprompt is defined as a combination of API definitions, coding instructions, and example code snippets. The API definitions are written in Python and include class, method, and function definitions. Code snippets are provided for each function and method, calling them at least once. The framework utilizes a single frozen LLM, which does not require comprehensive fine-tuning. The code generation module is defined using the LLM, which takes a preprompt and input question as input and generates a code that returns the answer to the question. The execution engine, in this case, the Python execution engine, executes the generated code with the input image to produce the answer. The notation and settings for visual programmatic models, VPMs, are also introduced. A VPM aims to generate a code that returns the answer to a question about an input image. The process is divided into two steps: code generation and execution. The code generation step generates a code using a code generation module, and the execution step executes the code with the input image to produce the answer. The preprompt definition is crucial in providing the LLM with detailed instructions on how to use the APIs. The preprompt includes API definitions, coding instructions, and example code snippets. The structural aggregation function inserts code snippets immediately after function definitions as comments. The authors introduce a novel coding instruction that provides concise guidelines for writing code, specifying a programming language and API usage. This instruction is designed to guide the generation of code that answers a given query. To address the limitations of previous visual programming models, the authors propose an adaptive prompt compression method to reduce the input token length of the code generation module. The compression phase involves a two-step process. First, API definitions are compressed by rewriting them using a frozen large language model and an instruction to rewrite API definitions. Then, code snippets are compressed by generating code specialized for each question type using the original preprompt, an instruction to write code snippets, and an additional instruction to write code specialized for a specific question type. The inference phase generates code to answer the input question by utilizing a compressed preprompt adaptively selected based on the question type. This phase consists of 4 steps: question classification, preprompt generation, code generation, and execution. Question classification predicts the question type using a classification prompt and a large language model. Preprompt generation produces a compressed preprompt given the question type using the compressed API definitions, coding instruction, and compressed code snippets. Code generation produces a Python code using the compressed preprompt and the input question. Finally, the execution step obtains the predicted answer by executing the generated code. The authors formulate the AdaCoder module by combining the equations for question classification and preprompt generation into the equation for code generation. The AdaCoder module takes an input question and generates a code to answer it by adaptively selecting a compressed preprompt based on the question type. AdaCoder is an adaptive prompt compression method for programmatic visual question answering, introduced to address the limitations of conventional code generation modules. The method is designed to work with 5 question types in the GQA dataset: object existence, object category, object attributes, relationships, and global questions. AdaCoder generates code as z equals pi ada, q, where the total token length is given by equation 13. A key advantage of AdaCoder is its adaptiveness, which reduces the computational cost of code generation. Although it appears computationally more expensive than conventional methods, AdaCoder improves computational efficiency in practice when using black box language models like GPT or Claude. This is because AdaCoder reduces the token length while preserving the structure of code, making it more efficient and effective than previous prompt compression methods like LLM Lingua. The authors evaluate the performance of AdaCoder using 3 VQA datasets: GQA, VQA-v2, and NLVR2. They use exact match accuracy and reduction rate of input token length as evaluation metrics, comparing AdaCoder to baselines ViperGPT and LLM Lingua. The implementation of AdaCoder is built on top of the official implementation of ViperGPT, using GPT and Claude as language models. The authors provide implementation details, including the API set consisting of basic image and text processing functions, and the auxiliary function set. The language models used, GPT and Claude, are also described. Experimental results show that AdaCoder reduces the input token length by 71.1% while improving QA accuracy on all three datasets, outperforming the ViperGPT baseline and LLM Lingua. This demonstrates the effectiveness and efficiency of the proposed prompt compression method. The comparison of AdaCoder with other methods, including ViperGPT, LLM Lingua, and simple compression, showcases its effectiveness in question classification and code generation. The importance of question type classification is highlighted, demonstrating that using ground truth question types achieves the best performance. The analysis emphasizes the significance of the instruction prompt for specializing code snippets, leading to better code completion. Additionally, the compression performance of API definitions and code snippets results in a significant reduction in token length and computational time. The ablation study confirms the synergistic effect of both compression components on QA accuracy. AdaCoder is a groundbreaking approach to compressing input prompts for programmatic visual question answering tasks. By adapting prompts based on the specific question type, it significantly reduces the token length and number of characters in the input prompts. This method combines API definitions, code snippets, and instruction components to achieve this compression. An ablation study was conducted to evaluate the effectiveness of different components in their approach, revealing that compressing API definitions and code snippets both contributed to improved performance, with a reduction in token length by 72.6% and 83.1%, respectively. Using a single specialized prompt for each question type resulted in better performance compared to using a fixed prompt across all question types. An error analysis showed that the predominant type of error was wrong answers, and AdaCoder reduced their frequency. However, there is still a 7.8% incidence of coding errors, suggesting room for improvement in instructing large language models about API usage. Overall, AdaCoder demonstrates the potential for adaptive prompt compression to enhance the efficiency and accuracy of programmatic visual question answering systems. Figure 7 presents qualitative examples of programs generated using AdaCoder, a framework that leverages a large language model, LLM, with a compressed API definition to produce Python programs for question answering. The input consists of questions and images, which are fed into the LLM to adaptively select example code snippets. These snippets are then used to generate a program that is executed to derive the answer, with intermediate outputs visualized to illustrate the process. Table 8 provides an error analysis of the generated programs, categorizing errors into 7 types. Correct but with unnecessary details, correct except for articles, correct by paraphrasing, coding errors, inability to answer simple queries, no object detection, and wrong answers. The results show that AdaCoder and ViperGPT have similar error rates, with the majority of errors attributed to wrong answers. The paper also evaluates the generalizability of AdaCoder across various multimodal tasks, including visual grounding, counting, relative depth estimation, visual reasoning, image editing, and object tagging. Table 9 demonstrates that AdaCoder consistently outperforms baseline models in all these tasks, with significant improvements. AdaCoder's key innovation lies in its adaptive prompt compression for visual programmatic models, efficiently generating programs for visual question answering by compressing and selecting prompts depending on the question type. Notably, a single black box LLM is employed to perform question type classification, textual compression, and code generation, eliminating the need for additional training. The authors acknowledge limitations and identify areas for future work, highlighting the potential of AdaCoder as a versatile framework for multimodal task solving. The limitations of AdaCoder's reliance on black box LLMs are discussed, highlighting the need for alternative choices, such as open source white box models. Future research directions include exploring the combination of white box and black box LLMs, pushing the boundaries of multimodal automated programming, and developing methods for interactive code modification. The automatic extension of APIs to facilitate their evolution is also seen as a critical step. The page discusses advancements in visual question answering, scene text visual question answering, and language models. It highlights the work of Ukai et al. On Llama 2, which introduces open foundation and fine-tuned chat models. Qingqing Wang's work on reasoning ability in scene text visual question answering and David Wingate's research on prompt compression and toxicity reduction in language models are also mentioned.